Hi, I'm Kilo, and welcome to this video series called Succeeding in Circuit Theory. This is the first video in the series, and it's labelled Voltages and Currents. Now, basic circuit theory is not that difficult, but there is a very steep learning curve when approaching it for the first time. This video series aims to cover the basics with an emphasis on common errors and how to avoid them. So let's look at the common errors. On the screen here, we have two circuit diagrams. The upper circuit diagram is reasonably straightforward, and the lower circuit diagram is a little bit less straightforward. Now, if you find that you tend to get the correct answers when analysing circuits at the top, but have difficulties getting the correct answers when analysing circuits like that at the bottom, then it could well be that these videos may be of use to you. So let's look at the things that tend to go wrong. The first and one of the most important ones is directions. Every voltage and current in a circuit has a direction, and if you get one of those wrong near the beginning of a problem, then everything will just go downhill and you won't have any chance of getting a correct answer. Multipliers. In electrical engineering, we tend to use the SI units. That means milli is times 10 to the minus 3, kilo is times 10 to the 3, mega is times 10 to the 6. Now, it's quite common for people to just use the actual SI designation, the M, the K, the capital M, etc. That's fine, but what actually causes problems for a lot of people who are starting out is when you actually just start cancelling out things. So, say I'm dealing with volts and I'm using kiloohms, then our currents tend to come out as milliamps. I'm not going to do that in this series of videos because I think it can be a little bit confusing for people who are just starting out. Not drawing circuit diagrams out and not updating your drawings with new information as it's calculated. In circuit theory, the actual theory itself isn't particularly difficult, but everything starts becoming quite complex. So it's a bit hard to keep a handle on all the information that you're calculating. The best place to do this is usually the circuit diagram. It captures the complexity of the system quite well, and if you record all of your values as you work them out onto it, and if you make any changes to it, you record them on it as well, then you'll be in good stead for being successful. Incorrect assumptions and trying to do too much at once. We all like our problems to be nice and simple and straightforward and for us to do it in one big step. However, as I said before, these problems can get a bit complex, and it's really a mistake to actually try and calculate them in one big go. You're probably better off just doing calculations step at a time, just one step at a time, and you just go through the steps, and by the time you get to the end, you will have the correct answer, rather than just trying to jump the gun. Mistaking component arrangements. Now, you've probably at this point already done some circuit theory, so you already know what parallel, series, etc. are. It's very, very easy to actually make mistakes there. That being said, it's also very easy to get it correct every single time, and in these videos, I'll actually go through a methodical way of determining whether things are parallel, series, or if they're neither. A voltage in a circuit is the potential difference between 2 points in that circuit. It can be shown in various ways, but we're going to concentrate on one way of representing it. I'll show you the other ways, but I'll then tell you why I think it's not such a good idea to use them. The most important thing, and this is common with all of the ways, is that the polarity and the direction of the voltage is always recorded. So let's look at our preferred way, where they're measuring the voltage across a resistor. If we look at the minus and the plus, that's where we're either calculating or measuring it. Right? And this is saying that we have 3 volts across the resistor, and that from here, from the plus, minus the minus, the voltage is 3 volts. So the plus side with respect to the minus is 3 volts. Now, if we do this, We've actually swapped the plus and the minuses around, but we actually have a negative number in the middle here as well. So let's just read this one literally. This is minus here, so the plus minus the minus is actually a negative number. So on the left-hand side resistor, we have plus to plus, so we have the left-hand side of the resistor is positive. On this resistor, we have a minus, so our plus is actually the negative end of the resistor. So whatever the sign you see in front of the actual number, that basically will go on where the plus symbol is. So we have a negative here, and we have positive voltage here. So this voltage minus that one equals -3. So this end is the negative end, this end is the positive end. This end is the negative end, this end is the positive end. The voltages across these two resistors are identical. This is just another way of representing them. Now, with actual numbers, this is probably a bit contrived, but if you actually had the 3 volts and you knew which end was plus and minus, you just write it on there like this. You wouldn't bother doing this. However, what you might have is you might actually calculate the voltage across this resistor with this being the V and the plus and minus there. You might actually be constrained. And so you then have to work out your answer, and your answer would be negative. So given that, let's look at a couple of non-recommended ways of doing it. The reason that I'm going to go through this is you might see these in other books or videos or whatever, and so you need to be familiar with them, although I'd suggest that you don't actually copy them. Right, this one is reasonably common, but again, it's not recommended, and it's basically to use an arrow instead of a plus and the minus, and the arrow goes next to the resistor. So it goes next to the component. In this case, with the arrow pointing towards the left and a positive number here, we would have our plus on the left and the minus on the right. So the plus symbol goes to the tip of the arrow. So it's exactly the same as the previous page. The reason we don't use this, or I especially don't recommend it, is because we use arrows for currents. And so if you're using arrows for currents and arrows for voltages, the chance of making a mistake increases. So I would suggest not to use arrows for voltages. So that's basically what this looks like. That's what we would replace it with. That's what we would prefer to use. Another system is a voltage reference to ground. Now this symbol down here on the left-hand side is either ground or earth, whatever you want to call it, is basically your reference point of the circuit, and it is 0 volts. It represents 0 volts. So we have 0 volts all the way along here, all the way up there. If you see an earth symbol and then you see voltage symbols or numbers with voltages on them, without pluses and minuses or arrows or anything like that, then this is in fact referred to that voltage. So we have a plus here, a minus there, V2. Just like this. This is how we would draw it. Plus, minus, V2. A voltage source is a 2-terminal device that can maintain a fixed value of voltage. An ideal voltage source will maintain this voltage for any value of current flowing from it or into it. So if we look at a diagram down here, if we have current flowing out any value or current flowing in any value, we will still maintain our 10 volts across these terminals. A voltage source must never be short-circuited. A short circuit is basically when we draw a line straight across here. So if we put a wire straight across the terminals of a voltage source, in essence, a short circuit is 0 volts. By definition, 0 volts across it. You have 10 volts here, you have 0 volts, you have a big problem. Likewise, if we put another voltage source across it with a different value, we would also have a big problem. So that's something that you also shouldn't do. In this series of videos, we'll always show sources as being circles and measuring devices as being squares, just to make it obvious. Now, we can have a very large voltage source with very small currents, and we can also have very small voltage sources with very large currents. It depends upon the load that we put onto it. There is no rule about the direction of current in a voltage source. It can flow either in or out. It depends on the rest of this circuit. If we look at this circuit that's shown, we have a voltage source that's 10 volts, and we have another voltage source over here that's 20 volts. Now this current, I1, depends purely upon the values of these resistors. And it can be actually a positive or negative number depending upon the values of these resistors. So it's very, very important. The only thing that's defined when you have a voltage source is the voltage. The current is an unknown. So now that we've gone over how we prefer to actually record voltages, we might as well actually take some measurements. I'm going to do the measurements in a simulator in a second, and I'm going to go through how to actually attach the voltmeter across a resistor to measure the voltage that is requested exactly. Now, this is the circuit that we're going to do. Okay, and we are going to measure the value of V1, and we're going to get its polarity correct. Now, the way you hook up a voltmeter to measure the voltage across component is very, very simple. We've got the plus here. We want to attach it to the positive end of the voltmeter. Typically, this would be labelled with a V. It's very, very common. Sometimes a plus, but most often a V. The minus end of the voltmeter will go to the minus end of the component that we want to measure, and that will be usually marked with COM, which stands for common. Right? It's also sometimes marked low and things like that, or minus, but V and COM are very, very common. So we're going to put our voltmeter across here. Here's the drawing of what we'll do. So positive end of the voltmeter, go to the plus end, minus end of the voltmeter will go to the minus end, and whatever that voltmeter reads, including its polarity, that's what V1 will be. So here's the simulator that I'm going to use today. This simulator is called Tinkercad. It's a free online simulator. It's quite nice for just very, very simple circuits because you can lay things out. It shows you the actual sort of what the actual components look like. You can hook things up on breadboards, etc. It's only very, very basic though, and it's so basic that it doesn't even work for AC circuits. It's supposed to, but it definitely doesn't work. Okay, so anyway, we're going to use this to measure the voltage across that resistor with our plus to there and our minus to there. I've set our voltage supply to 10 volts. I will set this now to a voltmeter and put the plus to that end of the resistor. I'll make that red. The minus to the other end of the resistor, and I'll make that black. So we've basically hooked it up exactly as we drew it in our diagram. And now if we start our simulation, V1 is negative 588 millivolts. So let's just record that now. I'll show you how to record it. So as I'm recording it, we had negative 588. Rather than putting millivolts, I'm actually going to put times 10 to the minus 3 volts. So V1 would say is negative 588 times 10 to the minus 3 volts. And if we were just doing further calculations around the circuit, it might just make our life a little bit easier if we were to swap those around and write 588 times 10 to the minus 3 as a positive. And that's it. We've successfully measured and recorded our voltage value, including polarity. Current in a circuit is merely a charge that's flowing through the components. It should be shown as an arrow flowing through the component with the value of the current above it. So here on the bottom of the screen, you can see two examples. which are identical. We have the current I1, positive I1, is going from left to right through the resistor, and we have the current negative I1 going from right to left. That's basically just two ways of drawing exactly the same thing. There is another way that you might see it drawn, which is definitely not recommended, which is basically with an arrow above the line or above the components with the value on it. The reason that we don't like doing this is because sometimes you'll see voltages as arrows above the line, even though we don't like to do that either. Now, current flows around a circuit in closed loops. If we look at our diagram here, we can see that these red things are our loops. So we can actually have a current can go around. Basically, it's got to meet up where it started without folding back on itself. So if we did this, that's not a loop because we would have folded back on ourselves. It's complete, like a circle, but it doesn't have to be circular shape. So we have a current loop here, so we can have a current flowing, and we've got one here. However, there's no way in the world we can actually draw a current loop through this component. So if we did that, we would have to go back on itself, and the same as going across here. It would be different if, say, we had another resistor here, then we could have another current loop. We could draw through there, another one through there, and then we could have one that goes across there. But as it stands, no current will flow through that resistor. Likewise, if we have a circuit here that has disconnected terminals on the output, we cannot draw a loop around it. And that means that we will have 0 amps flowing in this circuit. Unless we put something across those terminals, we will have 0 amps. A current source is a 2-terminal device that can maintain a fixed value of current flowing through it. An ideal current source will maintain this current for any value of voltage across its terminals. A current source must not be open circuited. Okay, so it's basically like the opposite of a voltage source. We have a current source down here. It's drawn with a circle with an arrow pointing in the direction of its current. So we have 10 amps flowing here. The voltage here is unknown. It depends totally upon the circuit that we've attached our current source to. The only thing that's defined is that current. Now, if we open circuited this, so if we remove this unknown circuit, then we would have our 10 amps source, but we would not be able to draw a loop. And if we couldn't draw a loop, then we have 0 amps. So we have 10 amps, 0 amps. They're both flowing at the same time. That's obviously a real problem, and it must be avoided at all costs. Another thing that we should avoid is putting another current source with a different value in series with the current source. It's similar to the voltage source in that its defined value is set, and the other value, in this case the voltage, it could have a plus or minus value and any magnitude depending upon the circuit that it's attached to. Now we'll talk about measuring currents. To measure a current, we actually need to put our ammeter in series with the component. So to do that, we actually need to break the circuit. That's our circuit from before. We want to measure the current that's flowing through the 5 kilo ohm resistor from left to right. And to do that, we will need to insert an ammeter as shown there. Now you note that the ammeter does not go in parallel with the resistor. That will give you a totally wrong value and can actually end up damaging your circuit and the ammeter. In this particular case, I don't think it'll make any real damage, but still. So what we need to do first, to go from the left-hand side to the right-hand side, is we need to disconnect our 5 kilo ohm resistor, one end of it, from all parts of the circuit. We have to pull out, in this case it's just one wire, we would remove that. We would then put our ammeter in, we'd connect our ammeter up to that end, and then there. So let's go and do that. So here's our circuit from before. We have our voltmeter and our bridge. Now I've got to turn this to an ammeter. And I will disconnect. So we want our plus to go to this side. It'll be easier for me to go up here. I'm just going to go to there. And our negative side to go there. For an ammeter, the plus side is often marked amps, milliamps, something like that. And again, the negative side is often marked common or perhaps low, something like that. So now at this point, let's look at it. We have our circuit and the current that goes through this 5 kilo ohm resistor, all of it must flow in this direction. So all of it must flow from here through the ammeter and then through the resistor. So we look at that and we have a negative current and it's negative 118 microamps. So now we've got our previous circuit up and we have our I1, and our I1 is equal to negative 118 times 10 to the minus 6 amps. Now again, remember that even though I see micro on the screen, I'm actually putting in the full multiplier each time. It'll help reduce the chance of mistakes in calculations later on if you do that. So if we go to our drawing up here, we have minus 118 times 10 to the minus 6 amps is the current flowing in that direction, which if we wanted to draw it the other way, we would draw an arrow there and we would write 118 times 10 to the minus 6 positive. Okay, we'll just leave it that way. That's our measurement taken and recorded correctly. Okay, now I'm going to show you a very, very common mistake that people make when they're making current measurements. In this case, what I'm going to do is I'm going to put an ammeter just across the resistor itself. Right? Now, this is an example of what not to do. And you can see that when we do this, we actually have a totally different current. It's not minus 118 microamps, we have minus 400 microamps. And that is because the ammeter is a very, very low resistance. Ideally, it's 0 ohms. So we are basically just shorting out this 5 kilo ohm resistor in the middle here. So it's a very, very bad thing to do. It can, in fact, in real circuits, you can end up, because you get larger currents, if you put it across the supply here, we could, in fact, damage the ammeter totally. So it's something that you should not do, is put ammeters in just in parallel. Remember that to put an ammeter in, you need to break the circuit first. You don't put it in just with 2 wires across things once the circuit's built. Okay, so that's the end of the video on voltages and currents. It might seem like we were just sort of doing really, really simple stuff, but if you actually manage to get your directions correct every time and get your multipliers correct, then you'll find that your calculations tend to start coming out with more correct answers than you would before. The next video in this series is Ohm's Law, and in that we'll actually start performing calculations, so it'll probably get a bit more interesting. Thanks for watching, and I'll see you next time. Okay, Kill Ohm out.